the heat won't overheat, we hope. But if there is a fire, in the unlikely event of a fire, I've been told that the big exit's obviously that side. If the fire's over there, then we exit that way and we can be led out to the front of the building. This meeting is being recorded. I think I need to press got it. And there we go. There we go, we're back there. Right, okay, so looking back on the project, just a few words about the project more broadly, and then we'll focus on what's been going on here at Caste Penrhyn. So the project is called the Dŵr Isca project, and you might be thinking, well, what does Dŵr Isca mean? Well, that's the, we chose the acronym because the title is quite long, okay? But there's a good reason for the name. Dŵr is obviously the Welsh word for water, and Isca is the Irish word for water. So water, essentially. And therefore, as you can imagine, the focus of the project has very much been on the water sector, opportunities to recover heat at various stages of the water industry, but also from large users of water, and that's why we are here today. Just a few words from me. If this works, okay, hopefully not sticking put the laser in his eye. Okay, so we've had several demonstration plants throughout this project, demonstration projects if you like, and we've had various events to showcase what we've been up to. Due to COVID, some of these were disrupted and they've happened a bit later and so on. We've had several very successful online events, and obviously some joining us today. And another big focus of this project is working with external partners. So I think the world of research in universities often, I think, is quite insular and we only talk to each other. I'm a big believer, and know others on the project are big believers in working with people from outside the university sector, with industry and so forth. And it's been great to partner up with the National Trust. We've got a partnership going back many years now, and it's fantastic for us to be able to capitalise on what we have on the doorstep from Bangor University in Caste Penrhyn here. So quite an exciting and interesting project. Obviously the castle here is a big user of water, and we thought there was an opportunity to maybe implement some quite nifty technical solutions or answers that could help us recover some of that heat that is lost from all the water that goes down the drain. And I'm here to say much more about the technical aspects in a minute. Sitting down, just very briefly, that's the kind of running order of the day. This is all very informal, and we want good discussion and chats. This isn't a formal presentation at all, but that's the kind of running order of the morning, if you like. We'll be here for a while, we'll hear a few presentations, we'll get a chance to go and visit the system that's been implemented here, and of course plenty of time for discussion. And you know, I guess 6 years ago when this project started, who would have thought that we would be in the position that we are, where there is so much concern about the volume, about the use of energy in general, but you know, the cost of energy, the environmental cost and economic cost, and water, heating water, the use of water takes up a lot of energy. So it's more timely, this project is more timely and topical now than ever, because as we will hear and see in a minute, there are very exciting opportunities out there for savings in terms of carbon savings and economic savings, if we actually manage the way we use our water a bit differently. So, you know, it's very exciting, very topical, very timely, and hopefully it's work that will make a bit of difference as well. It's a day for celebration and even a few balloons, okay, because it's the culmination of a lot of work. You'll see some posters around us here. There's been a lot of activity going on here at Caste Penrhyn, as well as with a whole range of other partners, and wanting to take the opportunity to show what we've been doing. sôn am lawer o'r pwyntiau yn barod, discussed many of these points before. Really, the idea is to look at how we can be a bit more efficient with regards to the energy use associated with the heating of water. And of course, with any demonstration plans, there is a need to tell people about what we've been doing and you know, what are the challenges as well as the answers and solutions to those challenges. And hopefully, of course, you know, the work can be extrapolated a bit further, and we plant a few seeds for others to take up in terms of ideas that they could implement. With those few words, I will leave you with this diagram, which shows you the many different elements of the project. We're just focusing on one or two of these today, but that's the Dwrish project in its all its glory, so to speak. So there's been many different angles. It's obviously a collaboration between us at the School of Natural Sciences at Penrhyn University, and working very closely now for years with partners that we have over here from Ireland. Great to welcome our Irish cousins over again from Trinity College Dublin, and their expertise is in the world of engineering and in the world of business, and you'll hear much more about that later on. So we complement each other nicely, because our expertise at Bangor University in the School of Natural Sciences is environmental assessments and life cycle assessments and carbon footprinting and so on. So many different angles to the project. I'm not going to go through them all, and we'll hear much more about one through them as we go. Felly, efo chydig eiriau yna, i ddod ar sgwrs I ben, I'll bring it to an end by a bit, but sort of reaching over to policy and to consumers and customers and industry and so on. As I said, it's a big element of this particular project. Okay, I'll hand over to Angus.
Yeah, thank you. We skipped in the system of slides, so we're going to get a little introduction. So Paul, you want to jump over there? Yes, go ahead. And if you can stand here,
yeah. So firstly, apologies, I've left my coat on because we're really energy efficient in Penrhyn, so it's cold in here. Who am I? I'm what's known in the National Trust sense as a consultancy manager. So hints in the title, I manage a team of consultants who help general managers such as Kerry and the operational staff with all aspects. So it's building surveyors, archaeologists, climate environmental advisors, etc., etc. I suppose my brief introduction is to do a bit of a scene setter from our perspective for the day. So we've been working with Bangor University for quite some time. My colleague Keith Jones, who's got COVID, so can't be here today, unfortunately. But we started a discussion probably in around 2015 with yourself, Crystal and Angus, to look at part of the programme of work we'd been undertaking in the Trust. We called it something called Fit for the Future. So in a nutshell, it was to develop an environmental management system for everything we did. We're a conservation charity, and the expectation is that if anybody asks us to show or talk about what we do in the Trust, the answer at the time was, well, of course, we're the National Trust, of course we're environmentally sound and our credentials are brilliant. But not to labour the point, if somebody actually called us out on it, what evidence did we have to show that we were doing all of the things we said we were doing? So part of this discussion built on the back of a programme of, in a nutshell, energy, water, waste, and making sure we were getting rid of that waste legally and compliant. That's culminated in contextual sense of we've made about 40% energy reductions across our whole portfolio of properties in Wales. We've now integrated over 100 renewable energy systems, whether it be hydros, biomass, heat pumps, you name it, we've got it. And part of the challenge was to dispel the myths in places such as Penrhyn Castle that you can't do anything. And part of this trial, when we were talking to yourselves, was to go, we can do something, because fundamentally it may be the second biggest building in the whole National Trust. But when it was built and designed, it's just a big house. and it just runs like a big house. It has inputs, throughputs, and outputs. So the elephant in the room as we progressed was around water. So in the National Trust overall, we bring in about 1 million cubic meters of water every year to what we call our enterprises, our food and beverage, our catering, our operational to support the tea and sticky bun emporiums, basically. Everybody comes for a nice day out, we'll have a tea and a coffee. So as far as it goes, in a Wales context, and at Penrhyn particularly, that equates to about 15,000 cubic meters of water coming onto this site for our food and beverage outlets every single year. Now that comes onto the site, so we're paying for the privilege of the water. We're then pumping it up the hill using electricity to get it to the castle, because they tend to build castles on top of hills. And then we have to heat that water, and it leaves in people in cups of tea and coffee, but it also does dishwashing and all of those other facilities that you think about. And the potential of going, well, we've brought it in, we've used electricity, we're heating that water, and we've got a biomass boiler here now, so we're heating it better now than we were previously and more efficiently with 7 individual oil boilers. But then we're then using it and pumping it straight through the drains, leaving all of that latent heat that's still within the water, that we're then having to turn around those tanks again to do the next lot of dishwashing, the next lot of tea and sticky buns, and that 20% of energy is lost. So that was the premise. We wanted to look at that trial here. Again, contextually, I won't steal the thunder from later in the day again. This is just one of 300 plus castles and mansions that the whole National Trust looks after. So think here and times it by 300. We've got 29,000 other buildings that we look after. So that's not just our enterprises side, that's also our residential, it's our farmlets, it's our holiday cottages, it's all the other buildings that are either in hand or working via tenants with partners. The potential's huge. And I'll shush now, but basically the language we use in the National Trust, and Kerry will understand this, I think, is memberships. We're a membership conservation organisation. We all know how hard it is to recruit a member and then to retain that member to our cause to support that conservation. So if you look at the facts and figures just for here, that equates to about 200 memberships per year leaving the site down the drains. So that's complete wastage, not only in wear and tear and energy usage to get it here in the first place, but going out the drains and we're not using it. So again, part of the findings for me of going, this might be one small microcosm of a trial and a test, but if you escalate that across the whole organisation, that 1 million cubic metres of water, that equates to 2,500, 3,000 memberships. And that's the core element of how we support our charitable cause. So I suppose as a scene setter, that's why I'm really interested in the findings today, and rolling forwards, how can we do more of that to stop wasting the energy and wasting the money, especially in the current economic position we find ourselves in, but translate it back to supporting our core purpose, which is conservation.
Okay, so thank you very much, Paul. It's very important for us to get the context of this from the point of view of the end user. Just checking that the online system is still working fine, and yeah, we're okay. So my name is Angus McNabole. I'm from the engineering school in Trinity, and I'm just going to basically agree with everything Paul just said by showing you the numbers behind all of this. And so I'll give you some of the technical information, and maybe be surprised at how much of the energy is wasted, and you'll see later on in the day the actual system. So let me see if I can do this correctly. Yeah. So I'm going to go through a little bit of the context and then the journey towards installing the system. So when you go and see it, you'll see a you know, in technology installed beside the kitchen, but it wasn't simply a case of taking it and putting it there. We had to kind of find the place to locate this. So there was a little bit of a journey along the way, and then the results of all of that. So there's some figures up here that show there's lots of as we already established, Professor mentioned and Paul mentioned, lots of waste energy going down the drain. Typically 15 to 30% of the thermal energy in wastewater is still embedded as it goes down the drain. So you can think about it if you were boiling a pot of pasta, what you do with the water afterwards, and most of it is that heat has gone down the drain. You're not pouring boiling water down the drain, but it's temperature hot water. And showers, another example. I showered this morning at 40 degrees, what goes down the drain is 30 degrees. And that's happening in all kinds of buildings, in the domestic sector, in the commercial sector, in cafes and restaurants, and swimming pools, and industrial fruit processing everywhere. And one of the things we did in the Durishka project, which is separate to what we're talking about now, is to try and assess how much of all of that is there. And in the UK commercial hospitality sector, that's 1.4 terawatt hours per year, which it's hard to put those kind of figures into context, but that's a lot of waste heat you could capture. So we'll come back to that figure later on. Now, I mentioned we're going to say a little bit about the journey. So we started off as a research project, as Professor set the scene earlier on, looking into ways of saving energy connected with water use. And water use we're focused on here is water heating. And so we were looking for ways of trying out this idea of recovering waste heat from wastewater. And we had a relationship with the National Trust, and we were to try and convince them that we could possibly demonstrate this at some of your sites. Now, a key person who isn't here today was Keith Jones, who we didn't really have to work very hard in order to convince the National, and essentially Keith did that for us within the National Trust organization. So without Keith, I think we wouldn't have achieved any of the stuff that has been there today. So Keith opened an awful lot of doors for us. And so the doors that he opened, a variety of suggestions were we had to go measuring where is this waste heat in the National Trust properties. So that involved measuring waste heat at a number of properties, not just here, other places, but also in this site. This is a very big site. We started measuring down in the car park where there are septic tanks. It's the first place we were trying to do it, and I'll explain why later, but also in the sewer network between here and there, and at various places within the castle, until eventually we found the commercial kitchen or the tea rooms, because it had ticked many boxes for us that again was later on. So it was a journey of trying to find the amount of waste heat that would prove to be economically viable after a few years of running. So now, before I go on to that further, I just wanted to mention, for anyone that isn't familiar with the concept, it is a very simple concept, but simply the idea of recovering heat from wastewater is that we replace part of the drain with some kind of a heat exchanger. And this little animation is taken from the actual commercial unit. So one of the things we used here is a commercial unit designed for showers, and replace the drain pipes are normally some kind of a plastic, which is an insulator, keeps the heat inside by to a certain extent, with a conductive metal like copper, or it could be stainless steel or something else. And the cold water that comes into the property passes through this and gets warmed up a little bit. And so when we let that cold water arrive in, we don't have to heat it as much to the temperature that we want to use it at. So it preheats the cold water with the wastewater going out. And there are a variety of ways of achieving that, but that's essentially the way a heat exchanger works. Now, next thing to consider, there are lots of places where we could try and recover waste heat. So the shower example on the previous slide is an example of doing waste in my shower and recover the heat. The advantage of that is I'm very close to where the wastewater is hot. If I move a little bit further away from that, the wastewater cools down. But so, for example, if I try to capture all of the wastewater in the building with a heat exchanger, I'll get more of it. But I'll be further away from where that waste heat is generated. So it cools down by the time it goes from the shower to the collection point outside. But there'll be more waste heat density outside altogether. So there'll be a larger volume. So the important thing in the energy available in wastewater is the volume of the water and the temperature. And as you move away from the dishwasher and sink and so on, the temperature goes down, but the volume goes up. And somewhere in the sewer system, there is a balance between where is the best place to capture all of that. Most of the energy available, if we were able to capture it, is in wastewater treatment plants. So here we have megawatts of heat that we could recover, which you would think, well, by the time it gets to the wastewater treatment works, it'll have lost all its heat. But it's still a little bit warmer than ambient temperature, and the volume is very large. Whereas in the component or the level, this is sort of kilowatts of heat. So there's an order of scale between the two. So what we've done here in the capsule is basically somewhere between these two. It's not capturing the whole building, which is what we tried to do in the beginning. And we'll see in a second, I'll have a little map to show where we started. We tried to capture the waste heat for the whole building, but too much of it was lost along the way as following our survey. But we're capturing the waste heat not from a single process, but from a few in the kitchen. So that's that one. So this is an aerial shot of the castle, and we're somewhere in here in this main park. But we start down here in the car park, where the main septic tanks are. So all of the wastewater goes down. There's quite a steep drop between these 2 points. We started monitoring down there, and we said, well, if we can recover the heat here, we'll capture everything in the castle. But that proved unsuccessful for a variety of reasons. There were, with an old building, leaks and all kinds of things and along the way that it didn't seem like it would be possible there. So we monitored at various places and ended up settling on the kitchen. The reason for the kitchen was that, well, it has high heat density and that we're very close to the point at which the waste water is hot and hasn't lost its temperature. We're very close. Another important factor, a practical factor, we're quite close to the heating system. So if we recover this heat, we need to do something with it. It has to be integrated into the existing heating system. And if those two things are far apart, then we'll lose heat along the way. So when you go to see the system, where we recover the heat is maybe 3 or 4 meters away from where we put it back into the castle. So in some places, hotels and businesses, the distance between those two could be far apart, which would reduce not necessarily make it not viable, but would reduce the viability. And then we also had a vertical space for the type of heat exchanger that we were using. In terms of research, there were two things that we were trying to do here. One was to use an existing commercially available heat exchanger designed for showers. And if you imagine in a kitchen, there's a different type of wastewater. So we weren't sure whether this would work or be blocked up and so on. The other thing is to do with a buffer tank, which I'll get to in a minute. But in the case of this heat exchanger, for it to work well, it has to be vertical because wastewater flows in a pipe. It mostly contains air with a little bit of wastewater in it. When it's vertical, the wastewater flows around the outside like this. Imagine the film flow and it drops down the edges. And the heat exchange happens around the outside of the pipe. That makes it work very well. If that system is horizontal like this, then the wastewater sits in the bottom and it's not very effective. So in the castle here, this is where the old drain was, and we happen to have enough vertical space below the kitchen to install this commercial unit. The kitchen is kind of, you'll see this later on, up here behind that lovely stone wall. Inside, let's say the next photo is a view from in this kind of darkened space, looking at the red box there. We replaced the drain, so the drain, I guess, used to end here with a plastic pipe connecting to the bottom. So you can see a whole series of copper pipes. So what we've got there is essentially 2 heat exchangers. One is dropping down here, and then the second one going down vertically. All the other pipes going along the top are connecting the cold water to flow through the heat exchanger and carry over to a buffer tank. And so basically, if we were looking at this and turned around 180 degrees into a room behind it, we would see a little room containing next 2 important elements of the system, which is the buffer tank. And the buffer tank is basically stores the heat that we save. Now, not absolutely necessary to have that, but we tried to store that heat because there's a delay between when you generate wastewater, hot wastewater, when you might need to use hot clean water. Not necessarily at the same time. So we try to store the waste heat in here. And then that's when it's required, goes into, you can't quite see it here, but I have another picture, the heating interface unit that links that in with the main heating loop of the castle. So, the system, right, so we designed it to try and assess the heat exchangers that I mentioned and the use of a buffer tank. We have it instrumented to monitor its performance over the long term. And it was supposed to do online communication, which many of my researchers know it partially did. The castle walls are very thick, and sometimes the Wi-Fi got through and sometimes it didn't. So we had to visit quite a few times. And we have a couple of different configurations of the system to test different ways of running it. It's a very technical looking diagram here, but essentially the way that we developed the system was we had two heat exchangers, so this is the symbol of one heat exchanger here, and another, a buffer tank, and then a heat exchange unit. Those three elements together, we were able to try and assess the use of the heat exchanger on its own, heat exchanger plus the buffer tank, and then all three together. That's the idea of this. And maybe why we do that, using just the heat exchanger is a cheaper system, but possibly not as much performance, whereas using the buffer tank costs a little bit more, but, you know, sustain a lot of lower performance or a better performance. So how did it all go? Well, it was commissioned in built in 2019, commissioned in February 2020. Perfect timing for all the tours that took place in March 2020. It did run for the month of February 2020. We actually haven't shown here, we have the data for that, but it was roughly stopped. So then we had a long period of nothing happening, and as of this year, we captured the full tourist season. So here at Penrhyn Castle, closest part of the year, so we're only interested in the point in which it's open and the kitchen is working. And so this is just showing you the variation in temperature, and this is a lot of data squashed into one graph. You can imagine there's a variation. There's no, there's no wastewater generation at night when the kitchen is closed and so on. But interesting things to note, for example, so the wastewater going down the drain, the red line is up, you know, reaching 60 degrees at times, and then at other times when it's nighttime or closed, it's closer to ambient temperature, 10, 15 degrees. And then there is a rise in that to do with ambient temperature across the year. So you can see that the lower end of the graph over there is colder. You know, this time of year, we're not dropping below 20 degrees in some of the cases, right? So in terms of energy then, that converts into so many kilowatts of power saved per day. And again, there's a lot of data squashed here into when I'll summarize the important bits of what does this mean in terms of payback and savings and costs in a minute. One of the things that we could have done better in the system is you'll notice there's a few minus figures here. In that the way the system that we set it up first is that the loop which circulates this cold water around is constantly going. So even when at nighttime and weekends and so on, when there isn't heat to be recovered, that water is still circulating around. So we're actually losing some of the heat in some of those cases. So an improvement of the system, if we were to make it in future, would be to have some kind of a smart on-off system for that little pump. I'll show you that when we go there later on. But it didn't lose us too much. And then there's another important element is this heating interface unit, and the buffer tank was a surprisingly useful piece of equipment. So the heating interface unit existed already, but it's essentially a heat exchange system itself. And this is a heat exchanger between our buffer tank and the main heating loop, and essentially mixing those two together. So that's right beside our buffer tank. And so this is a plot of the temperature, for example, in the buffer tank across the last year. And you can see that it is maintained it's obviously doing a very good job. It's maintained a very decent temperature throughout the year, despite the fact that the castle is closed at weekends and so on. It still isn't particularly cooling. Probably we're not presenting a lot of data on it, but one of the biggest factors here on affecting the performance of the system like this is the ambient temperature. So when the ambient temperature goes up, it loses less heat to the environment and vice versa. That's what affects this the most. you know, what's happening in the kitchen is much more constant in terms of the performance. So then how did it all go? We've got some figures here to show you the summary of the whole lot. So going from 25th of February to the 9th of September, which is the data we're summarizing here, it's still going on with 197 days, saved 1,500 kilowatt hours. On average, 233 per month. And there wasn't enormous variation from one month to the next. Now the castle is powered, or the heating loop for the castle is powered by a biomass boiler, and that costs, from the data we got from ENFIS, 9p per kilowatt hour this year. And last year I approximated what it might be. I didn't know the exact figure, but it was less last year, 4.2. So in terms of the system, it costs 1,800 or close to 2,000 pounds. And in the table here, we have the payback period, considering just the heat savings, for biomass and then for some other fuel types. So if we didn't have the current energy crisis and everybody's power was coming from biomass, well, we'd say, well, this is probably not really that viable with a 16-year payback based on last year's energy. This year, for biomass, we have a payback of 7.5 years, which is still fairly long. But we would hope that the current energy prices are not going to be the new norm, that they will go back down. But at the same time, I don't think that biomass boilers are very common, you know, in the hospitality sector in general, and it's more commonly gas and electricity and oil and so on. And so put those up just for the wider context of all this. So the worst one being current electricity prices, or versus last year's gas prices. You can get the idea of the amount of energy saved. There was a small amount of pumping costs saved, 3.1 kilowatt hours per month, but it's very small, so I just left it out of the table there. Essentially, the biomass boiler is down at the car park, for those who are not familiar, and that heat is pumped up here. And so if you require less pumping of heat because there's some saving going on, there's a small amount of pumping saved, but because that heats the whole castle as opposed to just the kitchen, that doesn't make an enormous difference. So those are the energy savings. Now, I just going back to the point that Paul made earlier about the, you know, I think you mentioned 300 other properties or kitchens or to that effect. So here, one kitchen where we're saved in the bones of a year, 1,500 kilowatt hours. But back to the point I made earlier, so when we study the whole hospitality sector in the UK, the estimated energy that's wasted is 1.4 terawatt hours. And so you'd have to, if you were to do the sums, how many Penrhyn castles or kitchens that, of course, they're not all of the same size, some are going to be bigger. There's an awful lot of opportunities to save heat, you know, in that. And I put a statistic in the bottom from the Irish context, you know, considering the domestic market, similarly, there's a large scope for potential for all of that. So that gives you the technical side. I think I'm going to hand over to Isabel to talk about the environmental impact.
Thank you for the introduction. Good morning, everyone. My name is Isabel. I'm a postdoc on the Duration project here in Bangor. And what I'm going to present you now was part of my PhD, which I also did here in the project. So you've heard how the system works, about the technical side of things, and also the financial benefits. And now we're going to talk about the environmental benefits, because this is a major reason why we're recovering heat. There are also some trade-offs from the heat recovery system, but I can tell you the environmental trade-offs are very low compared to the benefits. So as everything you produce, every product, and also the heat recovery installation first comes with an environmental footprint, because it has to be manufactured. So if you look at the life cycle of our heat recovery system, then, for example, the heat exchanger, which is from copper, has to be manufactured. So the life cycle of the heat exchanger actually starts, for example, with a copper ore, which has to be extracted, and then the double-walled copper pipe has to be manufactured. and fittings have to be manufactured. And we also need pipework to connect the heat exchanger with the boiler or the heat interface unit, for example. Insulation has to be manufactured, packaging, we have to transport it to Penrhyn Castle, for example. And then at the end of its life, most of it is usually recycled, but parts of it will, for example, go to landfill. So there is an environmental footprint connected with it. So in the beginning, we are extracting resources, and we also need energy for manufacturing for the whole life cycle. And at every stage of the life cycle, emissions are created, emissions that are going to air, to water, and to soil. And there is a methodology which I use, which is called life cycle assessment. And this life cycle assessment quantifies all these emissions. And according to the damage that these emissions create, they are categorized into different environmental categories. And the most important and famous one you've all heard of is climate change, of course, but there are other environmental impacts that can be looked at in the life cycle assessment, which are, for example, eutrophications and overload of nutrients, basically ecotoxicity, so toxic substances, and also resource depletion, which is the consumption of resources. So in our case, we consume metals or also fossil resources wherever we use fossil energy. And on the other hand, we have the benefits, which I told you are bigger than the impacts from the system. So I looked at different heating energy sources, which would be replaced by the recovered heat. So for example, gas, electricity, or in our case at Penrhyn Castle, it's wood chips and solar thermal energy, geothermal energy, and also looked at the mix in the UK service sector that is used, the energy mix that's used for heating water. And we have also for the production of generation of those heat sources, we also have the consumption of resources from nature, and we need energy, for example, to cut wood and to transport it to Penrhyn Castle, for example. And also here we have emissions that are created, but we avoid those because we recover heat. So what I did basically is comparing the impacts from the system to the benefits in different cases. And there are several factors that influence this comparison, these pros and cons. So for example, on the side of the heat recovery system, it depends, do we use copper or maybe different materials? In the future, heat exchangers might be in this form, might be available from other materials, such as plastic materials. Also, it's beneficial if a lot of the copper is recycled copper. And then for the pipe work, it can be from copper, like in the Penrhyn case, but we could also use steel or polyethylene. And the footprint of the system also is influenced by the amount I need. So how long is this pipe work? On the other hand, our environmental savings depend on how much heat I can actually recover. So in bigger kitchens, I can recover more heat, and I have bigger benefits than in smaller kitchens. And so to the first results, let's look first at just at the impact of the system. And the example I'm showing here is a copper heat exchanger, which is made from 35% from recycled copper, which is the average rate for copper materials in Europe. And 10 meters of pipework, which is the easiest configuration in the simplest one, also here at Penrhyn Castle. And I disregard a buffer tank in this scenario because it's not necessary. It also works without one. And basically, so here are the impacts for a couple of categories, and we can focus just on climate change for now. Anyway, you see they're very similar, the bars. And basically the results are that most of the impacts really come from the copper parts. So here the yellow one is the heat exchanger, and the light blue one is the 10 meters of pipework. And other parts of the life cycle, such as the insulations manufacturing or fittings or transport and packaging and end of life, only plays a minor role in the environmental impacts. And now to the other options that we would have. So for example, in our case, as I said, it's a copper heat exchanger, again, results for climate change. But in the future, for example, there are nowadays heat exchanger materials available that use polypropylene as a base, so it's a plastic material, and then they are enhanced with graphite, for example, to enhance the heat exchange. And we see here, okay, in the future, if we look, if we use other materials for the heat exchange, then we can even lower the impact from the heat exchange system. And it's similar for the pipework that we install. It's we have less impacts if the pipework is shorter, obviously, and also steel or polyethylene pipes can have a benefit or less impacts compared to copper. So it's important to look at the design of the system as well to minimize the environmental impacts. Yeah, so now let's compare a bit with the environmental benefits that we have. So in the case here of Penrhyn Castle, as Angus said, it's about 230 kilowatt hour per month of heat that we save, so 2,760 a year. And if we compare, if we express these in the environmental savings, then, so I'm just showing it here for climate change, so for greenhouse gas emission savings, then in the case of Penrhyn, it's about 300 kilograms CO2 equivalent, which is saved, because we're replacing mostly wood and a little bit of electricity, as Angus has said, which is from pumping less water up to the castle. However, if another kitchen, for example, that has the same amount of kilowatt hour savings but uses natural gas, or the UK electricity grid mix, then the savings are even higher. And if we look at the payback time, so that this is environmental payback times, it's similar to financial payback times, but we look at the environmental impacts which are paid back. Then if we look, for example, here again at greenhouse gas emissions, well, these are in years, so it's basically less than a year for basically no matter which energy source is replaced. For solar, it's with more than a year, but also very, very low, considering that the lifetime of the system. So I have considered a lifetime of 10 years, but that's quite conservative. And however, if we look at, for example, resource depletion, so the resources that we use in the installation of the heat recovery system take a bit longer to be paid back by the resource savings from the energy savings. So it's about, for wood, for example, it's about 30 years. So these are the little trade-offs which I mentioned, that especially there are smaller kitchens that don't recover a lot of heat, and this part of the environmental payback takes a bit longer. So we also look not only at the Penrhyn case, but also at other kitchens and other kitchen sizes. So this graph shows the environmental, so in this case, the climate change impact per kilowatt hour of either recovered heat, these first three bars, which you can almost not see, and other heating energy sources per kilowatt hour. So the good news is that you can almost not see the bars, which means the impact of recovering heat is very, very, very little compared to the impact of other heating sources. So natural gas used to pay electricity grid mix, wood chips, geothermal energy, solar thermal energy, or the mix of energy that's used in the service sector. And just for your reference, so the first bar is the Penrhyn case, and then we have this bar is, the red one is for a small kitchen that doesn't recover a lot of heat. So it's taken from the flow rates that we find in UK commercial kitchens. And yeah, in a large kitchen, you can basically not see the bar because it's so small, the impact, because a lot of heat is recovered there. So for the mitigation of climate change, there are always benefits for recovering heat, no matter how big or how small the kitchen is, and no matter which energy source is replaced. I now show you the results for resource depletion, where I also already told you there's a little bit of trade-offs. which you can find for very small kitchens. So this time, if we look at the smallest end of commercial kitchens in the UK, then we can see that the impact of, sorry, that's the red bar, and then we can see that the impact of recovering heat, depending on which energy source is replaced, can be a bit higher. But if we look at all the kitchens in the UK, then these smaller ones where from an environmental point of view, recovering heat might not be sensible, is only about 10%. So it's really the majority of kitchens where the environmental benefits are much greater than the impacts. And if we look at the, say, average system as it is installed at Penrhyn Castle, then from about 170 cubic meter per year, we can say that environmental benefits are given even for in resource depletion, for example. Yeah, and if every kitchen in the UK was to install a heat recovery system, and then the emission savings per year would equal about 500,000 tons of CO2 equivalent a year. And that's what equal taking 260,000 cars off the road approximately. We have also developed a calculator for kitchens, for commercial kitchens to use, because as you have seen, there are a couple of factors that influence this comparison and influence the benefits and the environmental benefits and also financial benefits. So this calculator enables the kitchen to get a first estimate of, is it really sustainable in my kitchen, and also financially viable? It's an Excel-based tool. It's available for free on our website. I guess we can send around this link after today to all the participants. So yeah, it takes into account individual factors of the kitchen, such as the water consumption in that kitchen, for example, or the kind of energy that's replaced. And it's just a little insight into what results you can get out from the toolkit. So it shows you the heat that's recovered per year, or for example, after 10 years lifetime. You can also customize some values. That's why you see 2 bars here. It also shows environmental savings, for example, for the greenhouse gas emission or carbon savings. So this is a case, an example for a mid-sized kitchen, looking at the UK commercial kitchens, where, well, the carbon payback time or climate change payback time is very, very small, so small that doesn't appear when you round it to this number. And then also gives you a financial insight. So what are the savings per year after the lifetime, and also what the costs are. So the capital costs for heat exchanger or the pipe work. So it takes into account how long, for example, is the distance between your heat exchanger and the boiler. And in this example, the financial payback time would be about 2 years. Yeah, and this is it from my side. If you have any pressing questions now, I guess I can take 1 or 2. If not, we have time afterwards as well for other questions. Okay, then I think we can continue. Thank you.
Well, good morning. Good morning. My name is Paul Conklin. I'm a member of the Trinity team that's been collaborating with our Welsh cousins in Bangor and our Welsh cousins here in Penrhyn over the past number of years in the project. What we're going to do in this section is just raise a few questions, and I'm inviting colleagues who are here in the room and colleagues who are online to share some questions, and we'll see if we can address them. But while you're getting your mind in order, there are 2 mindsets that have informed this project. One mindset, in a way, is drawn from the whole idea of lean manufacturing, where the Japanese, originators of that kind of thinking, would speak of searching for the last grain of rice in the lunchbox. It would be replicable and add up to something significant. And the second mindset is one of collaboration. Collaboration across the different discipline groups, but crucially, collaboration with practitioners as well. So the engagement and the collaboration with our friends, cousins in National Trust has been central to this project. And as a project, we could have started and finished within the laboratory, but we didn't. We could have started and finished as an individual. The engineers could have tackled it, as Angus explained. The environmental scientists could have tackled it, as Professor and Isabel explained, but we didn't do that. We came together and progressed the work out of the laboratory and into practice with all of the unexpected issues that arise there. So maybe if I could ask, I'm not sure now how we will do this with the arrangement we have here, but if I ask Angus to come back up for a moment, just to ask him a particular question. How difficult, Angus, was it to work with these other discipline groups and work with practitioners in order to achieve what we've seen demonstrated this morning?
Careful with your answer.
Yes, good question, Paul. I think that, of course, it's not personally difficult in any way. I've joined to work with all these people. I'll give you an answer of there are technical difficulties. We worked in the case of Penrhyn Castle and doing this from the idea to the actual system you see later on. But we also explored the idea with a variety of hotels and restaurants and similar settings across Ireland and the UK. And in some cases, it's not practically possible to do because of practical considerations that wouldn't appear in the lab, I guess, getting to your question. So things that I mentioned a little bit earlier on were like the location of the waste heat and the location of the heating, the clean heating, are not always in the same place. And so there's a practical, connecting those two won't always make economic sense, which means that some of that 1.4 terawatt hours is not necessarily economically viable. Turn it around. But if you persist, there are lots of ways of trying to find a solution. Similarly, there are practical limitations around the heat exchanger. So the particular design we use requires that space underneath it, which isn't always there. And there are alternative systems around. There are lots of choices for that. So, does that answer your?
It does. And if I could ask Paul to come up, you sit down. I'll get you up again in a moment, Angus. Paul, so participating in a project like this, National Trust, as you explained to us earlier, has many properties and many opportunities to collaborate. What was interesting for you and your colleagues and keep in collaborating with this project, this Durishka project, which has spanned a number of years and has seen 2 demonstrations of technology here in Penrhyn this morning, but in Timor with microhydropower?
Well, I think building on what you've just said, partly it was also looking at what we can do in an appropriate sense. So we've got constraints here. It's a listed historic building, for example. We've got medieval villages. We've got Richard will know much better than I about the constraints we have to work in. So partly from mine and Keith's side, it was dispelling those myths, going, if you take what people would perceive as a hard to treat building and you can actually appropriate integrate solutions, then why aren't we? It's not rocket science. Why are we? And it does lead on to your grain of rice of going those ever decreasing circles of effort versus output. least we can have a look and see if it's achievable in an appropriate sense, but also achievable in a payback sense.
Yes.
So for me, that's what made it interesting.
Yeah, very good. And had you collaborated with other funded projects like this? Because this project had European funding, Ireland, Wales funding, which of course has been central to the collaboration that has taken
We'd
place.
started to investigate it, I have to be honest,
Mhm.
but there were challenges. So I suppose on running parallel with this and running on the back of some of this, what it did for us was open the doors for others to become interested.
Mhm.
So one of the outcomes for us is, as we started to progress integrating some of these solutions, we found a lot of our time was talking about the solutions we'd integrated rather than doing more of them. So on the back of that, we developed something called the Fit for the Future Network, which using evidence from this and actually practitioner end focused, was rather than all of you approach the problem in isolation and reinvent the wheel every single time, this network, which now has, I don't know, about 120 or so members across the UK and Europe, what it's allowed us to do is have a forum where we could share, but also, to put it bluntly, to enthuse and get that sort of, well, if we can do it here and we can work with partners like yourselves and we can look at funding opportunities, then what that's done for us is open doors to more opportunities. So I would say yes, but it was always back to the elephant in the room of going, where do we start?
Yeah.
Whereas the proactive approach of this one is going, go on then, let's have a go.
Yeah.
It served a purpose, definitely for us.
Brilliant. And let's have a go. And if I thank you, Paul, and I call you back. And Isabel, if I ask you to come up for a moment, and how valuable has it been for you and Prisora and your colleagues in Bangor, but in particular in the environmental science area, to have access and to have the opportunity to contribute to this kind of a project?
Well, the big benefit really is when looking at environmental and at environmental impacts, or doing a study such as I presented. It's usually difficult to get such data, for example, from literature from somewhere else. So it's well, on the one hand side, really good to have real world data, basically. And also for me, as I don't have an engineering background, so it was very valuable to have engineering colleagues, but also to be able to see how it looks like, which materials are used at the installation, because often we find studies that only rely on literature data to be far away from real world results. So this was great. I mean, the collaboration with other disciplines, and then also seeing it how it looks realized.
Were you able to teach the engineers something about the environmental scientist's perspective?
Well, I hope so.
And did you learn anything about engineering?
Yeah, a lot. I mean, I learned a lot about heat recovery and heat recovery materials, and I mean how which components you need to do it, and what the obstacles are as well, obviously, and what you have to look at.
And that kind of overlapping between the discipline groups and the practitioners is actually central to making something like this work. I'm wondering if there are any questions immediately. Thank you, Isabel. Any questions immediately? Madam? Yeah, good. Do you want to shoot the question? And
yes, so we have a question for both Angus and I'd say Isabel. So I think the question is from Nora. Is it Campbell?
Nora Campbell. Good morning, Nora.
Good morning, Nora. So I think the question was, I think she said your life cycle analysis was very interesting, Isabel. And maybe a question for maybe all three of you. It was along the lines of how could this sort of recovery be implemented on a wider scale, maybe across the whole of Wales, perhaps? Like, how would you see such a rollout of scaling up happen?
Okay. You want to come up and interrange, and I'll step out for a moment.
So how can this be implemented on a wider scale? So I guess something I did when I was sitting down and thinking afterwards, something I didn't mention during the slides is to emphasize to everyone is what we've done here or what we have done here in Penrhyn is in a small kitchen, quite a small kitchen. So the performance and the payback should be seen in the context of it's a small kitchen. So if it was a little bit of a larger hotel restaurant or something, you know, probably that would be the economic viability that would be better. So there's probably quite a good case for just a, you know, if there were, and there are some companies doing this commercially, for it to be an investment that can pay for itself and market activity to go on. In other settings, then I mentioned the idea, for example, of doing this in wastewater treatment plants. If you could install it there, well, you would be recovering megawatts of heat. But the technology for doing that is not necessarily there. And also the use of megawatts of heat at a wastewater treatment plant is also, there's nothing generally there either. So if you could fix that, that would really scale up the problem quite enormously. That would require sort of district heating to be much more common, at least in Ireland and probably the UK as well, and some bigger heat recovery technology. Okay, so yeah.
Very good. And maybe if I follow in terms of replication, and I don't want to put you on the spot, but Anon is with us from a hotel close to us here in North Wales. And I'm wondering, Anne, to Nora's question about replication of this idea and maybe even components of this technology, as somebody who's involved in a family-run single hotel, but in quite an important tourist area. Do you see potential in that?
Definitely. So if you imagine our kitchen is probably the size of this room, no one's here.
Okay, yeah.
So I don't know how that compares with Penrhyn's kitchen.
We'll see that in a moment.
Okay. But there's also, we have 104 bedrooms with showers. And then we've got that, so I think the opportunities are definitely there.
Very good. And any other reaction from colleagues in the room, or any questions that you have?
I have a question, maybe for Paul and for Angus. I think so. We have a 2-year period where the system was installed during the pandemic, where, you know, there was a big drop off in both usable data and recoverable heat. So maybe a question overall, like, do we see it's a resource dependent on people using the tea rooms? So it's also like if the whole system is devoted to recovering heat and a large proportion of the heat is there, what if the people aren't there? What if there's how do you balance that?
Do you come in range?
So I suppose because I was thinking about this as well, and in a development sense, from what we're doing, I'm looking at this going, yes, it's a small trial and a small, you know, so how many visitor numbers on average do you get a year?
This year it's 130,000.
130. So if you
That's 130,000 in case you haven't heard. That's...
Sorry, 130,000 visitors here coming through that kitchen. We're still ramping up the sense, I suppose. So if you look 40 minutes down the road, Bodmin Garden, 350, 200, 300, 350,000 visitors a year. So if I'm looking at my business case for the development in not only in a financial sense, but in a triple bottom line sense, it stacks up, doesn't it? It's a £2,000 investment for 150,000 visitors to recover some of the heat. Now, if those visitors don't turn up on a Tuesday, that for whatever reason, then we're not generating the hot water demand. So actually it just balances off the equation, doesn't it? So I suppose in a broader sense, and maybe I've got a question following from it, sorry, is I'm looking at those other opportunity costs or opportunity savings. So when I started, I was talking about energy, water, waste and compliance. So I'm interested to see if you have, or if you haven't yet, could you look at some of the data in terms of that hot water and the grease that is integrated into the hot water is going down the hill. The heat exchangers slowing that hot water and recovering the heat. So actually, in terms of pure practical terms rather than technical terms, what we're seeing is a lot less grease entering into our sewage system or into our grease traps. So there's opportunity elements there in terms of managing the end, in terms of the settlement tank or the septic tank. Again, I'm not having to empty it as often because it's not getting clogged up with grease. So are we factoring in those other opportunity savings as well? So commercially, yes, energy makes sense, builds in, but when you start to look at the big picture, we're not actually capturing all of the opportunity from a small scale trial. What's the scale trial on 500,000 visitors and the grease that leaves the thing and flows down the hill and goes into the treatment plant, which means you have to empty the treatment plant 4 or 5 times a year. So I suppose it's, for me, it stacks up in that way of going 150,000 of it. If they didn't turn up, we wouldn't have grease, we wouldn't have energy use, we wouldn't have water use, and we wouldn't need to turn it on. The most efficient system is the one that's not on. But in terms of real terms, it's adding in all of those other aspects of it as well. Does that waffly answer the question?
Yeah, wonderful. And Paul, just as you are there, I think, you know, it's a hugely interesting listening to you like this, because what I'm getting the sense of is a question popping up in your mind as a result of the platform that's been created by this work.
Yeah.
That you might not have framed or articulated in the way in which you have. So one achievement like this leads to new questions,
Yes.
which in turn leads to new initiatives, and so on. And before you sit down, across the portfolio of properties within National Trust, how difficult, how easy, how open will your colleagues be to hearing about this story and considering what it means for them and their responsibilities?
That's really interesting, because we're looking at redeveloping the F&B outlet here, so the tea rooms here, and it might be in this room we're currently sat in, with an idea to the future and the growth. So already colleagues have been in touch with me going, it's the show and tell aspect of real evidence and real findings can start to inform our design decisions at an early stage, rather than previously going, we've no evidence to work with.
Yeah.
It's a lovely idea, but nobody can really show me.
And the facility is too difficult to work with.
And it's difficult, and we can't do it, and it takes up too much space, and what about, and what about? So for me, that's why it's posing questions now again. I think you've got a positive audience coming off the back of this, go, might not be able to do everything everywhere, but surely we can do something somewhere.
Yeah.
And just planting that seed in their brains for me is going, good, you're going to consider it, and at least the discussion is going to be had.
Yeah, yeah. That saying that was attributed to Barack Obama, yes, we can, and the Irish or the Gaelic version of that was is féidir ling. And Professor, what would the Welsh version of yes, we can be?
I'm going to go home and tell my wife I've just been compared to Barack Obama. That's amazing. Yeah, she won't believe it. Thank you.
Great stuff. Thank you, Paul. Please.
Can I just ask where you think of Greece? Sorry, where do you think the Greece is from? Is it going into treatment?
So we do have grease traps here. So it is getting trapped in there. Yeah. But obviously, it's without getting all technical, it's got to be a certain distance from the point of entering the drains, because it's got to have time to cool down, solidify a bit, get trapped in the grease traps. So this is the challenge we face, certainly in a historic setting. You go, where can we dig a hole to put a grease trap? Because archaeology central, this building's this, historic person is that. So for me, cooling the water down is one step along the journey. So actually, there's less energy that's bypass the system, even if you've got one. So it's all positive.
We have self-catering cottages, and until we change the behaviour of the general public,
It's changing the menus as well.
whatever, that you've been trying to persuade them not to put the oil, grease down the drain while the water is hot. It might get to your treatment plant and it will be taken out, whatever, attention. But it's not going down the drain, mixed with water. It's going to be settling all your practice, all the way down.
So it's finding the sweet spot of where you then put your grease into centre.
Okay. Good. So to wrap up this part of our program, just one or two thank yous. First of all, thank you to Isabel and Angus and Paul for contributing some extra thoughts and reflections. Thanks to Anne for giving her perspective onto the question that we've just had about grease traps, and to Nora for her question online. But there is another acknowledgement that we need to make. And if you advance the screen, please, Madhu, and that's to our funding agency. You'll see that the European Regional Development Fund, and in particular the Ireland Wales Fund, has been central to the achievement of this collaboration and of this thinking, searching for the last grain of rice in the lunchbox. And over the years of working with them, it's been terrific because they have appreciated the exploratory nature of this work and supported both financially but with encouragement the collaboration that it has taken for us to do that. And it's terrific to have a funding agency that recognizes and values innovation, and innovation that arises from collaboration, not just across disciplinary boundaries on the researcher side, but collaboration also with the practitioners. And as you can see, there are tangible outcomes from this, which hopefully will, as they say, grow legs and find application outside in society in general, so that enterprises can benefit, but also society more generally can benefit from the environmental savings that have been demonstrated and that hopefully are in our collective future. So with that, I'd like to hand back to Prisor, and he will take us to the end of this phase of the program.
Thank you, Jeff Paul. I have one quick question as well, actually, just to Anne and Paul and anybody else. I mean, are you going to be rushing away from today thinking, you know, this is an investment we cannot refuse? I mean, the figures, both in terms of carbon savings and economic savings, are really impressive. So we're just thinking in terms of a legacy and for this project to grow legs and have, you know, make a proper impact. What are the barriers? I mean, is it something? Wales is a huge tourism industry and big ambitions to grow it further again. I mean, is it lack of awareness? Is it, you know, some kind of pump priming or grant aid? I mean, are there any messages that we can maybe feed back to Welsh Government or tourist sector and so on? I mean, how do we take this forward?
I'll definitely be asking for more information that I can pass on.
Yep.
Obviously, for any commercial business at the moment, cost.
Yeah, exactly.
Yeah. Particularly the cost, but then cost of energy.
Yeah.
Hopefully, this will go hand in hand. So,
Yeah.
but yeah, any grants or anything available would be amazing.
And raising awareness of the potential.
Yeah.
Yeah.
From our side, so discussions we've had with catering staff here is that we need to be integrating this system into our new developments for our new outlets, should we say. It's the awareness raising, I think, none of this is rocket science, I think, from what we said at the start. This isn't overthinking it, it's recovering the heat from a wastewater.
Yeah.
Don't overthink it. It's the bit where people get to the stage going, what does that actually look like?
Yeah, yeah.
What does that actually mean? What does that actually cost?
Mm.
And that's the industry going forward for me, going the technical engineering solution technologies there.
Yeah.
We've proven that.
Yeah.
What we need to do now is go, well, again, first remove the problem. If your boiler doesn't need to be on, you don't need to consume electricity. Or actually, when you are doing, we do it as efficiently as possible. Maybe that's a common prime thing from the government.
Yeah. Okay.
Use less, use it more efficiently. So it's getting the message out, it's communication.
Okay, thank you. Something for us to mull over tomorrow, I think. Really interesting. Thank you both. Well, right. So yes. So in terms of getting the message out, that leads us quite nicely onto what we've been trying to do and host, in holding this kind of event, and we have social media presence and a website and so on as well. So we are trying to disseminate the information widely. You've heard about Isabel's tool, an online tool that's free to use that you can plug in your own numbers and see, how this could work for you. So yes, spread the story. If you know of others who would be interested, then please do pass on our website details, and you can sign up to our newsletter that Roberta is in charge of and so on as well, and follow us on social media. So we're coming to the end of this bit here, really, and now is the time that we actually go to see what's been done in a very practical sense and have a walk and talk, and let's keep the conversations going. So I would like to thank you for coming. And Angus, do you want to?
Just sort of like before we wrap up there, so there's an online, for everybody else, there is an online 3D tour which Madhu is handling. We took some very nifty photos, and so the people online will go with Madhu to that. For those of us that haven't seen it already here and wants to go down, we'll arrange that. But beforehand, I think we have a speaker to give us a little history of the castle. Yes, yeah. And so if you want to go ahead and just on, it's just for the microphone here. Yeah. Go ahead. Thanks.
Welcome to Penrhyn Castle, our little discreet castle on the hill, as it were. There's been a building here since the 1400s, and the initial building was here for the Griffiths family, who were major landowners in North Wales at that time, who were connected in with the Princes of Gwynedd, so very influential in North Wales at the time. And they built the first house here, the medieval manor house that got the first name of Penrhyn Castle. They were here for several centuries, and then they passed the house on, or sold on to the Williams family. And then by the late 1700s, it's the Penrhyn's that come in and buy the estate and marry into the estate. The Penrhyn's are sugar merchants. Richard Penrhyn is the descendant of the original people of who went to Jamaica to set up plantations, and using enslaved labour in Jamaica. They created a massive fortune and left Jamaica as quickly as they could, and came to Britain, back to the UK, and set themselves up as sugar merchants in London and in Liverpool. They bought into this estate, and they were looking, and Richard Penrhyn particularly was looking for the next big thing. And the next big thing that he wanted to invest in was in this area of North Wales, and it was slate quarrying. Slate quarrying has happened here for centuries before then. It's been here since the Roman times, but it's been a very small industry. The big difficulty with slate is not getting it out of the ground. It's quite simple. Moving it, it's heavy, it's awkward. Moving it around was the limiting factor. So what he did was he invested in North Wales. He invested hugely with his sugar fortune into the infrastructure of North Wales. He built roads, he built hotels, he started a tourist industry. He built new houses. So he really invested. He created the starts of the big quarry in Bethesda that you see today. He also invested in the port just down the road that way. So the Abercegin port became Port Penrhyn, and that's when he started to export all around the world. And he also rebuilt the house. So in the 1780s, he built Penrhyn Castle No. 2, which was quite a large house. But he didn't spend too long worrying about that. He was always looking at new investment, new developments. He spent all the money he had on entrepreneurial stuff. So he was really keen on that piece of it. In fact, he spent so much money. This place was bankrupt when he died in 1808. £100,000 of debt he left his wife for the next 8 years. So she was living here in the old Penrhyn Castle, and the house itself and all of the land and wealth would eventually go to Richard Pennant's cousin. George Hay Dawkins Pennant spent 8 years fretting about this house that he was inheriting and working out what he wanted to do with it. What he wanted to do with it was build it even bigger. I always said I'm glad we didn't do the Penrhyn Castle number 4, because we'd probably be an island by now. But he decided that he was going to use his wealth and the investment that had gone into quarrying in North Wales to build this house. The investment and the wealth was on an absolutely astronomical scale. So we're talking about the start of the Industrial Revolution here. Everybody needs Welsh slates on their factories and their houses. So they are generating huge amounts of cash, just enormous amounts of cash. This place took about £100,000 to build. In a good year in the quarry, it was making £100,000 of profit. So it's enormous. The house is enormous to reflect that. It's not subtle. Nothing about the house is subtle, as you'll see as you go around the house. It is a demonstration of power, wealth, and influence. And it completes that task. Poor George Hay Dawkins only lived, but he enjoyed building. And then it then passes down to the Douglas Pennants, then marrying into the family. And they become the Lords Penrhyn. And they run the house as they wanted to, and as the house is designed to. It's an entertainment palace. It's not their main house. They're only here for 4 or 5 months in the year, so they've got other houses that they spend at the time in. So, but it does its job. So Colonel Edward Douglas Pennant inherits the house with fantastic parties, inviting royalty, which does its job. So he becomes Lord Penrhyn. He must have been a really good party for Queen Victoria a couple of years before then, because it becomes a noble. And then the house, much like the quarry itself, is a very boom and bust house. So very short period of time when it's running at its peak, and then it slides gently off into obscurity. The chief thing that we remember about the second Lord Penrhyn when he took over is the Great Strike. So the Great Strike happens in Bethesda, 1900 to 1903, is a lockout of the workers, decimates the community of Bethesda, and it still is felt very deeply even to this day. After that period, as you say, you know, he breaks the strike, he breaks the community of Bethesda, and it's never the same again. The quarry starts to decline. People don't want to spend that money on slate from this area of North Wales. So generally, it becomes smaller and smaller and smaller. And then when the fourth Lord dies in the 1940s, this house is then handed over to the National Trust through the Treasury and the acceptance and use scheme. So we've had here open since 1951. Unfortunately, you won't be able to see it as you go around the house, but even we, with the resources of the National Trust, struggle to maintain the house of this scale. So we have areas where you don't get to see where there's no floor, there's no ceiling. So it is a ridiculous edifice to try and maintain. But we open it to the public. We've been open to the public for 50 years. We're currently running the exhibition that you see through the house at the moment is the What a World exhibition. So that's looking at our colonial links, or the links of the collection pieces that we've got in the house across the world. So it's the wealth that buys these links across the world, and we've been working with local community and with school in Bangor to create poetry to talk about the things that you see around the house. The next bit that we're going to look at over the next few years is our interpretation around that slate story. So there's a few bits and pieces in at the moment, but we'll continue to do that story of the slate, and particularly talking about the industrial relations and the problems that have been had in that period after the Great Strike. So that's a quick run through of Penrhyn. It's a big building. There's lots to see, but if you want to go up to the front door, you can come around, have a look at what's open today, and I hope you enjoy Penrhyn Castle.
So we'll organize a tour. We have to divide it up into groups of maybe 4 because it's a small area. And for those that are interested, the National Trust have kindly provided a free pass to go around the rest of the castle, you know, in your own time afterwards, if you want. So you may have already done that, but the option is there. So, and Matt, are you handling the online?
Yeah.
So I can switch that. Yep. Okay.
Hello, everyone. Can you hear me all right? Both in the 3D tour and on the Zoom? Just give me a message on the chat or something if no one can hear me. So we have a bit of an issue with the people accessing this Hubs platform that we're using through institutional access. So if you're at home, you might find it easier to log in than if you're in the office. But as I said, I'm sharing my screen, so we'll start off with the tour here. If you hang on, I've just got a couple. All right. Yes. Thank you, everybody, for confirming. Thank you, Breda, Katrin, and Brendan. Okay, great. So let's get started. Yeah, and if people are in the lobby, you can just join room. I think once you're in the lobby, if you want to get in, it'll ask you you can change your name, you can choose a different avatar if you like. I can see that there's 3 or 4 people in the room at the moment. If you're in the room, you can use the arrow keys or WASD on your keyboards to move around, and you can use your mouse to look around the screen like I'm doing now. I'll stop moving around so much now because I guess I'm sharing my screen, so people might be a bit worried. All right, so thanks for joining us on the online tour, everyone. This is the cafe, the tea room, where we are recovering heat from. As you can see, the counter is right ahead there, where I'm looking at. Behind the counter, you can see the kitchen up there. And as any sort of tea room, there's a bit more seating over there. It's a very traditional type of Welsh tea room. You know, they have scones, tea, all of those things. And as we discussed about the castle, so we'll have a look through a couple of different aspects of the tea room and the castle. This 3D tour initially started off as an idea for us to have a digital artifact for our project. But now it's sort of become also a nice opportunity for us to showcase this demonstration site for people who are not able to attend in person. So, all right, so we'll start with the kitchen first, as we said. So we've got just so people have an idea of what the numbers for the people in the kitchen are, in case they want to have an idea of what sort of visitor numbers. So we've got a little graph just over here in the whiteboard. So if the people in the chat room are having a look there, so that's the customer numbers for the cafe across the early part of 2022, from March to about July. So you can see that on average, there's a couple of hundred at least, but with a peak of about 1,500 in April. That's probably around Easter, I'd say, and a lot of people in early summer as well, up to 1,000. So quite a few numbers of customers in the cafe, just so people have an idea of the sort of size we're dealing with here. And so that's basically generates a lot of hot wastewater in the kitchen. So that will predominantly be from, you know, washing dishes. So that would be most of the hot water. The hot water temperature is usually in the range of about 40 to 50 degrees. And we'll have a bit more of an idea of that when we go to the next site. All right. So we've got 4 different sites for the 3D tour. And this is the first one. And I'll just put in the next scene for us, which is my scenes. Which is the courtyard, or the courtyard as it's called here. Let's go through to the courtyard. All right. I'll ask everyone to just ignore the whiteboards for now. We'll play around with the whiteboards after. We're in the courtyard now, so we have a bit of a context for where we're going next. So this courtyard was built as a part of the expansion of the castle by the first Lord Penrhyn. I think it was built around 1870 or so with the expansions. It's basically just a yard for storing coal and wood for the servants' quarters. Now that window up there is the cafe where we were before. And where we're heading to now is where behind the curtain, as we'll say over there. If you might have seen the presentation, and that's where we had the heat exchangers and the pipe replaced underneath. And that's where we'll go in now. We're just here as a sort of in-between location before we go to the next scene, which is we'll come back here at the end, just so we have a bit of an idea of where we're going. So we're kind of in a courtyard next to and below the cafe, and now we'll go into the cellar where our heat exchangers are. If you have any questions along the way, please feel free to put it in the chat, or if you can unmute yourself and ask me the question, that's also completely fine. All right. Yeah, so it's just some funky colors whilst we're loading. I'll just move the fly mode. All right, great. All right. So now we're. Oops. I can't move. Okay, that's fine. All right, great. So here we are. So this is us underneath where the main kitchen drains are in the cellar. And as you can see, you might have seen the copper replacement for these drain pipes in Angus's presentation. But what we have here is a foam insulated version of the same copper pipe. It's just covered in foam now to prevent the heat from escaping and to make the heat transfer a bit more efficient. And so yeah, that's what we've got going on over there. So this is the actual section of the pipe. So the hot wastewater from the kitchen flows through the middle of this pipe, from the top to the bottom, just through the gravity. And we pump cold water along the outside of the pipe. It's sort of like a pipe within a pipe, essentially. So the cold water goes on the outside of the pipe and gets heated up by the hot wastewater that's coming down. And then that's circulated through a series of pipes, which you can see above, going through to the control room, which will be our next destination. Just so you have an idea of what the temperature ends up being. So as you can see through this little graph right in front of us here, we've got a temperature of about 20 to 21 degrees for the inlet of the cold water coming into the tank. This graph sort of shows us the evolution of the temperature throughout a day of operation. So it goes from about in the morning time when the cafe is not operating, we don't really see much of a difference between the inlet and outlet temperatures. But as the cafe operates more and more progressively throughout the day, you can see the temperature increasing throughout the day. So this is just for one single day. It's the 2nd of July, which was a sort of moderately busy day for the cafe. And you can see that the initial temperature of about 20 to 25 degrees of the inlet wastewater goes up to about 30 to 35 to 40 degrees even at times. Something you can see is that the inlet temperature sort of increases a little bit throughout the day as well. And that's just because we're constantly pumping from the buffer tank, which stores the cold water that's going, the preheated water that's going to go into the kitchen. And throughout the day, more and more heat builds up within that tank as well. So the inlet temperature increases as well because it's the same water that's being pumped around. You'll have a bit more of an idea when we go into the next room, which gives us a bit more of a clear idea of what's in the system. All right. Okay, great. And here we also have a few sensors you can see. So just so we know all the data that we have recorded, all the analysis that we've done, it's been through all these little sensors that are attached to the heat exchanger. They measure a whole different range of parameters, mostly temperature and flow. So we're particularly interested in the flow of water, the cold water going in, the cold water coming out, the flow of the hot water going through the pipes, and the temperature of all the different elements. We had a whole bunch of monitoring equipment as well, some of which you can see on the other side on the back here. So this is a whole range of monitoring and transmission equipment. It honestly gave us no end of troubles because the walls of the castle are really, really thick. These use mobile GSM, sort of mobile data signals to transfer the data around. And we had a lot of issues with both the transmission of these things, the operation of these things. We tried using external antennas, but ultimately we couldn't ever get the data to be accessible online. So in the end, we had to go down there to collect the data periodically. But this whole thing is a set of different monitoring equipments that we've used to record the different like sort of performance characteristics, which we all use to relate it. So it's not just to say that it's not important to just do the experiments, just to keep the data and then analyze it as well. All right, and the last place that we'll go to is the control room, where we'll have a final idea of what everything looks like. So, yeah, all right. So here's our last one over there. That's just loading a little bit there. All right. If you find yourself stuck at the bottom of the floor, like I can see some of you are, just point yourself upwards and move forward, and you should get out from underneath there. All right. Okay, so this is the control room of the cellar, and this is what Angus referred to as our buffer tank. So you can see there's a pump over here to the left-hand side of it. There's another pump to the right-hand side of it. So what the pump in the right-hand side did was it would pump the water within the tank out to the heat exchanger from up there, as you can see. And it would go to the bottom of the heat exchanger, come out from the top of the heat exchanger after having absorbed all the heat from the wastewater. And it would it comes back into the tank from underneath. And this pump continuously operated. And that's one of the things Angus mentioned could be improved upon we could have a better control of how that pump operates, just so that that's an improvement, because there's an electrical cost to running that pump. It ran continuously for the whole project, whilst it really didn't need to run on the weekends or when the cafe wasn't operating. And the other pump over here to the left-hand side is the supply pump. So it supplies the preheated water from this tank. So the tank temperature I think the energy is what we've got here. But Angus showed us the tank temperature. The tank temperature went up as high as 40 to 50, almost close to 50 degrees in summertime, more in the range of 30 to 40 degrees in the time of more like spring and late winter. So this supply pump pumps the preheated water within the pump to this thing here, which is what this white thing over there, which is the interface unit. And together with some of the water that was coming in from the biomass boiler that the castle had, this combined water from the tank and from the biomass boiler was, so based on the temperature, was sort of adjusted and mixed and sent to the kitchen for them to use, basically. And so that ended up saving quite a bit of energy and quite a bit of costs as well to the castle system, as we discussed. And basically what happens in this system is that the heat from the wastewater is always absorbed and put into the buffer tank. But the buffer tank isn't like a completely necessary part of the system. It was more of a trial in this case to see whether the buffer tank improved the situation, provided more energy overall. It did provide quite a bit of energy, and I think we're quite happy with how it worked. But the system could also just operate without the buffer tank, whereby the cold water that's coming into the system can be heated through the heat exchanger and go into the heating interface unit directly, and be mixed in and go through to the kitchens. I've got a graph over here as well to talk about a couple of things. So we've got another day of the system operating. So we've got two lines there. We've got the red line and the black line. So we have the red line, which is the power that would be required if there was no heat recovery being operated. So you can see it's in the range of about 4.5 kilowatts for the kitchen. And you can see that when along the day, there's a bit of variation. So obviously when the kitchen starts being used around 9:30 to 10, the power required to actually heat the water goes lower and lower as we recover more and more heat from the wastewater that's coming out. And at certain points, you can see that it's almost less than half the actual requirements. So it pulls it's a little bit variable. So we're always going to need a backup sort of system to provide the heat, but it's really good at reducing how much heat actually the backup system needs to provide, or how long the backup system needs to run to maintain that level of heat, if it's a boiler especially. And dropping the power from 4.5 to 2 kilowatts at certain times of the day is quite good. I'd say it drops it close to half. So that's very, very appreciable difference in terms of boiler run time. So if you ran your boiler half as often as you used to, or even a reduction in a certain amount, especially if it's an electric boiler, is a big saving. Now, this is basically the main part of our 3D tour. Now, I'm not sure how many people we have online, because not sure if I can't seem to see anybody in the actual room. But I'm not sure if people have either hidden themselves away or disappeared. But what I wanted to do at the end was see if we wanted to leave some comments, or if we wanted to take a photo. We'll have a final scene out here at the back down in the coal yard where the whiteboards are. So I'm just going to change the scene to that, and we'll see if we can find the other people in the room and take a couple of photos, if people don't mind. All right, so we've got one more person there, as you can see. If you would have joined the chat room, that's what it would end up looking like. And yeah, I just wanted to say a little bit of a thank you to everyone for listening. That's okay, Catherine, no problems. Thanks for that feedback. And yeah, I think I'll take a quick screenshot here. That's fine for me. Great. I was hoping to have these whiteboards as a bit of a small graffiti space, if people were able to get into the room. If you go onto your place and have the pen there, you can make a few marks along the line there, and yeah, go for your life there. And if anyone else is interested, or if you have any more questions, please feel free to ask them in the chat. But that's sort of the close to the end of our 3D tour. Do we have any questions? Are we happy with everything there? If you have any other questions about the system as well, as far as my knowledge goes, I can try to answer them as well. Okay, I'm just going to stop sharing my screen now because I can't really get a very good feel for everything there. Okay, thanks, Don. So Don's just asked us what the advantage of the buffer tank is. That's all right, Katrin. There are some issues with hubs. So Don, the advantage of the buffer tank is we can, what happens if there's no buffer tank is the cold water would recover a certain amount of heat. It would be very instantaneous and it would go through to be preheated. You would recover a significant portion of the heat, but it would only cover what happens with the buffer tank is we're able to store the heat for longer and build up to a higher temperature. So what we noticed was the buffer tank temperature, as we saw, it goes higher up during the end of the day. So there's certain points where you almost need very little like external heating to get it to a temperature of 50 degrees. Whilst if you just ran without the buffer tank itself, you would preheat to a certain extent all the time, but you'd never get to the stage where you could turn off the system for a little bit of time or turn off your preheating your alternative existing like heating system like the biomass boilers they have down here in Penrhyn. It is a bit more of an expense, but it sort of could result in better savings overall because you're able to store the heat and build it up as opposed to just quickly grab the heat to a certain extent, if that makes sense. No problems.
Thank
all
you.
right.
Thanks.
That's all right, Don. I think I've got, if you could do the survey that Roberta sent through before, I'll just put the link down at the bottom again as well. No problems, Breda. And yeah, if you could, yeah, to whoever we still have, if you could do the survey, we'd really appreciate it. And yeah, thank you very much. I think that would sort of brings us to the close of the online part of the meeting. And yeah, I'll just stay online for a little bit, see how that poll is going. And if you could do it, and if you have any other questions in the chat, that would be great. I'll turn off the recording now as well. All right. Thanks a lot, everybody who's stuck around. Yeah, I hope you enjoyed the 3D tour. We've got a couple of other more static 3D tours on the website as well. If you're interested, the website is Dwarishka. On our Dwarishka website, I think it's dwarishka.eu. And I'll put the website on as well. But yeah, and if you want to sign up to any of our newsletters, or if you want to sign up to hear more about our research as a cluster member, yeah, you can find those links for that on the website. All right. Thanks, everyone. And I'll stop recording there. All right.